Let's see, do I remember how to prove root 2 is irrational? Okay. Claim that root 2 is rational. So root 2 equals p over q, where p and q are integers. Q does not equal 0. And the greatest common divisor between p and q is 1. Basically meaning that you can't simplify them down anymore. So you wouldn't say p is 2 over 4. You would say it's 1 over 2. So I don't think they really need you to say this in the Leaving Cert proof. I'm not 100% sure, but it's supposed to be there. But anyways, if we square now, we get 2 equals p squared over q squared, which means 2q squared equals p squared, which means p is even, because p squared is even because p squared is 2 times an integer, so it has to be even, which means p is even. Because look at the square numbers, for example. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. The even square numbers were originally even numbers squared. So because p squared is even, we know that p is even, which means we know that we can say p equals 2m for some m integer. So what that means now is you can say that, I think you can then go back and say root 2 equals 2m over q. And if you square that, you get 2 equals 4m squared over q squared. Cancelling the 2 and bringing the q squared up, we get q squared equals 2m squared, which means q is even, which means q can be written as 2n, where n is an integer. But if p equals 2m and q equals 2n, that implies that they're both even, which means they have a common factor of 2, i.e. contradicting the claim. On line 1. Therefore, you can say root 2 cannot equal p over q, which means root 2 is not a rational number, which means root 2 is irrational. Okay, again, I'm sorry, I'm a little bit tired. I think this is how the proof goes. What I'm going to do is break this video up into 2 parts. I'll do the B part as a separate video. Just in case I got this wrong, I can re-upload it.